our second lecture by Andras. Two of them today, right?
Yes. Okay. Okay. So I was puzzled what to talk about, so I decided to do two lectures, one on cyber-Witten theory and the afternoon on Haggard third. I would like to give introductions and maybe focus on one theorem. Whether it was a good idea, you will be the judge. We'll see. So these are the tools you need to show that things do not exist in four-dimensional topology. That, for example, if you would like to prove exotica or an exotic property of a four-manifold, you would like to show that a certain diffeomorphism doesn't exist. And these are the tools to do that. So these are, how shall I say, very negative results. They certify what cannot happen. And so let's start with the cyber-Witten. So once again, X as before, closed, oriented, four-manifold. Every now and then, for simplicity, I will also assume that it's simply connected. So sometimes I1 is just trivial. That makes arguments a little simpler, but this is not so instrumental. And so what I would like to explain today is that how this function, the cyber-Witten function, is defined. And so the idea is very simple. You would like to distinguish smooth structures or manifolds. So, you would expect that differentiable functions are different for a pair of potentially exotic examples. How can you tell that? Well, you write down a PDE and you expect that this naturally defined PDE has a different number of solutions for your two examples. And this will be the distinction. It's much easier to say than actually to do it. And so here is what we have to do. So the first step is pick a metric on X, pick a metric G on X. So that will be the first auxiliary choice. And, it's easy to write down PDEs on manifolds. For example, the exterior differentiation, it's a fine PDE. And the problem is that when you consider the solution space or closed forms, and maybe you divide out by exact forms, so you do something tricky, then you get something which only depends on the topology. And we would like to go beyond that. The next idea would be to take, I don't know, the Laplacian, and that's fine. And you take the solutions. The solution set will depend on the chosen metric. So that's like too sensitive. So we have to find something in between. And it took quite some time to come up with the right operator. It was initiated by Simon Donaldson in the early 80s. And what I will tell you today happened in 94 when Seiberg and Witten had some groundbreaking work on understanding Donaldson's differential equation, and they came up with a new one, which is more topological in flavor at the beginning, but then, as you will see, there is a fair amount of analysis in it. So what do we do first? So pick a metric and pick a spin C structure on X. So what is it? So for me, a spin C structure is just so spin C, a pair of U2 bundles So these are just complex C2 bundles with a Hermitian metric, which we call W plus and W minus on X, satisfying two conditions. The first is that the determinant line bundles, these are now complex line bundles, should be isomorphic. And when you take this tensor product of W plus and the dual of W minus, you expect this to be a C4 bundle that should be isomorphic to the tangent bundle of X. Well, that's an R4 bundle, so when you complexify it. So that somehow this spin C structure is attached to the tangent bundle of X. So we will massage this isomorphism a little bit later on. This is what will give rise to the Clifford multiplication, which is very important in the theory. And when we put a metric on G, then the symmetric group of one tangent plane is SO4. So the symmetries, said differently, you can associate a principal SO4 bundle to the tangent bundle by taking the orthonormal oriented frame bundle. So this gives us PSO4 of X principal SO4 bundle. So this is just a bundle where all the fibers look like SO4, not exactly SO4, it's like an affine version of that Lie group. You don't specify the unit element. So this is the input coming from the metric. Well, the symmetry of such a situation, fiber-wise, is given by the spin C group. So this is a group which is not so difficult to describe. This is just U2, so these are pairs of 2 by 2 unitary matrices. These will give rise to these W plus and W minus with the constraint that their determinants should be the same. So let me just make a few remarks. So SO4 is a 6-dimensional group, right? 6-dimensional. So O2 is like, so SU2, if you remember, that's like the sphere, S3. So this is 3-dimensional, so this is 4. When we take 2 copies, this is 8, but we cut down with an equation, so this is a 7-dimensional group. And in the discussion, I hope you will discuss that, in fact, these 2 groups are related nicely. So indeed, spin C4 is the total space of the non-trivial S1 bundle over SO4. So this sentence contains 2 statements. First of all, there is only one non-trivial S1 bundle over SO4. You have to remember what classifies circle bundles over spaces, and this happens to be exactly the non-trivial S1 bundle. It's a little bit similar to the spin structure where you take the non-trivial Z2 bundles. So the real version of that would be the spin group. Question. Okay. All right. So this is the input, and then so we have to remember that when we have a Riemannian metric, then it defines as a Levi-Civita connection. So G provides a connection, the Levi-Civita. So you have to remember that the connection is like the extension of the concept of taking directional derivatives. You have to, we take a vector field, or more generally for a bundle, you take a section, and you have to take a tangent vector, and then you take the differentiation in that direction. Why is it called a connection? That's a different story. I will not talk about that today. Okay, so of course, if we have a connection on the tangent bundle, that comes from a connection on the principal bundle, and you will get an associated connection on every associated bundle. But now we have something a little bigger. So in terms of the principal bundles, we have this situation that we have SO4 X, and we are looking for a spin C4 bundle, or this situation just tells us a spin C4 bundle which completes this triangle. So if we have a connection on this bundle, on PSO4, we hope to get something on this other principal bundle by pulling it back, but it will not work so nicely. The point is that a connection on a principal bundle is just a one form with very special properties that in the fiber-wise, it should be an isomorphism. It should map into the Lie group of this group. No, sorry, the Lie algebra of this group, and it should be an isomorphism on the tangent bundles. But this is one dimension higher. So this is like an S1 bundle, and we have to do something about that. So in order to get the connection on this bundle, we need a further and another choice, namely a connection on some S1 bundle, which we luckily have one. So there is this bundle, and we have to pick a connection on there. So take A to be a connection on the determinant line bundle, which is the same or isomorphic to this guy. So these are now the ingredients we have, and now we are ready to actually write down this mysterious PDE, and it goes as follows. So the Levi-Civita plus this A gives a covariant differentiation on W plus this associated bundle. So we get, giving a map from the sections of this bundle together with the tangents to here. Okay, so this is for a covariant differentiation, you have to give me a section and a vector in the direction, and you just take the directional derivative on that. Well, this can be written a little differently by writing that, in fact, we are mapping from the space of sections to the space of the same sections times the duals, the cotangent vectors there. And now we come back to this condition, and again, we sort of flip it to the other side, and this will just give us combining. So this is what I will call, I don't know, nabla of A, combining with this with gamma plus tensor P star to gamma minus. So I sort of flip the star to put it on the other side, and then I take the dual of the tangent bundle. We get
Is that an arrow or a minus sign?
arrow. Sorry, we never subtract spaces of sections from each other. Not here. Yeah, there is this principle now in school, like, you don't take a square root of a negative number, and then you go to college and they say, oh, you can do that. And then they say that you never divide by 0. And then you go to college and they say never divide by 0. So it's completely inconsistent. Okay, so we get this covariant differentiation. Again, it has two components. We have to pick the metric, which gives the Levi-Civita, and we have to pick an auxiliary connection on another bundle. And we combine this, and we have an operator which goes from W plus through this to the sections of W minus. And the natural idea would be to take the solution space of that. So consider those phi's in gamma W plus, which satisfy that phi's, that this is 0. So this is a linear equation in phi. The solution set would be a vector space. And again, what are the problems? The first is that it will depend on the chosen metric, and also it depends on our chosen connection. And so what Seiberg and Witten did is they added one more equation, which is a little more complicated to describe, but let me just try. And notice that this was not so much of a 4-dimensional phenomenon. You can sort of run through the argument in any dimension and you would get this what's called a twisted Dirac operator. But now comes something truly 4-dimensional. And this starts with an observation that, so we take two forms on Rn, and this happens to be isomorphic to the Lie algebra of SON. So we have to remember that SON is just the n by n orthogonal matrices with determinant 1. And the Lie algebra is therefore, so their defining equation is this. So if you take the Lie algebra, those are those matrices which satisfy that A plus A transpose is 0, right? What is this identification? I wrote that down, but now I don't see. Oh, here it is. So how does an A, such a matrix, defines a 2 form? Well, you just take omega A for V and W to be equal to the scalar product of V and AW. And then it needs a little bit of a checking that indeed this property based on the property of A defines you a 2 form on Rn. So that is again not very special in for dimension 4. It holds in every dimension. But now comes the point that this Lie algebra is actually it's a simple algebra in every n except for 4. It splits into 2 pieces. The reason is that the universal cover, well, it's a double cover of SO4 is actually SU2 plus SU2. So somehow although the group SO4 itself is not the product of 2 Lie groups, but if you go to the double cover and the Lie algebra doesn't distinguish between your group and the universal cover, then it splits. So let me just give you the map from SU2 cross SU2 to SO4. So SU2 is like 2 by 2 unitary matrices with determinant 1. They correspond to, they are the same as unit quaternions. So these are just unit quaternions. This is sort of an amusing little exercise to do. It's very similar to saying that SO2, the special orthogonal group of 2 by 2 matrices, is the same as the unit complex numbers. It's exactly the same idea. And so how do I assign an element of SO4 to a pair of 2 unit quaternions? So these are 2 unit quaternions. Well, I will assign phi q plus q minus, which now maps from the quaternions to the quaternions and sends H, my favorite typical quaternion, to q plus H q minus inverse. Or conjugate, it doesn't matter, these are unit quaternions. So it takes a little bit of a computation to show that in fact, this is a 2-to-1 map. You can see who is in the kernel. So there is 1, 1 that will map to the identity, obviously, and -1 will also map to the identity. And you have to convince yourself that no one else does that. And of course, it has to be checked that it's really in SO4. So, well,
Right above the parentheses, you said Lee, SU, that should be SU2.
here,
SO2 or SU?
well, it doesn't matter.
Oh, SO3.
Sorry.
Okay.
So, yeah, SO3 and or SU2, or SO2, but that would be. So this sends you a message that if you want to see, to see in dimension 4, sort of you have to move your 2 eyeballs completely independently. These will don't do that at home. Okay, so that's great. What's so special about 2 forms? Well, there is one fantastic 2 form. Once you have a connection, then you can take its curvature, and the curvature will be a 2 form. So globally on X, we have splitting FA, which is just the curvature of A as a positive and a negative part, or a left or right, it doesn't matter. So we have an omega, then it can be decomposed as the sum of a positive and the negative side. And so this is what only happens in dimension 4, right? Because this splitting happens only in dimension 4, and then we have the following very mysterious equation. The first one was sort of natural, having the connections and taking this twisting dot operator, and now comes a less natural thing. We have, there is a map from spin C4 to SO3. Actually, there are 2 maps, sending the 2, you remember spin C4 is just pairs of unitary matrices with equal determinant. And we can take them, we can take the following. So phi AB, which sends the vector V to AVA inverse. And then there is this friend, which sends it to B inverse. And so these will again be on instead of the quaternions, we just take them on the imaginary quaternions. And here is a fact.
Excuse me, can you write the part a bit bigger, the part 2 phi?
So AB is sent to phi AB. And this will be a little sloppy. So we would like to have a map from the imaginary quaternions to imaginary quaternions. And I will write it like V is sent to AV VA inverse. There is a little cheating here because in fact, these are only U2 matrices, but in order to have this interpretation, what I did, you have to have an SU2 matrix. So you have to divide by the determinant, but you sort of do it twice. So that's fine. And there is another version when you use the B. And the fact is that taking the first representation, so this is phi and there is psi. B, and the fact is that using phi, we get the associated bundle lambda plus of X. So these are, and with psi, we get lambda minus of X, where lambda plus lambda minus is just lambda 2 of X. So again, this is just the reflection of how this principle splits not only the two forms around 4, but globally the two forms on X. I'm not sure how much I confuse you, but so here is the lesson. So you have all these concepts like these groups. What you really have to do is first to get to know the groups. The groups are SO3, SO4, SU2, and then their combinations. And there is this principle which should be sort of taken as the main reason for all these invariants to exist. And then there is some little representation theory, like when you associate bundles to the principal spin C4 bundle, then what do you get? And I will not go into the details of why these happen, but this is sort of a catalog of the phenomena. And where are we? Yes, and so there is a map, sigma, mapping from age to in age, sending quaternion age to minus age I age bar. Okay, so on age, on the quaternions, we have representations of spin C4 on both these, and the claim is that this is equivariant if we use the representations, and now I have to check which one. So so we have this representation, let's call it I don't know, mu plus, or I call it phi, q plus q minus on age, and this one on in age. So this is just to say that using this sigma, we can turn phi in W plus to an element of lambda plus of X. So we can go from a section of this bundle to a section of this bundle. So this leads us to the following. So can consider FA plus. So remember, this curvature 2 form splits as a positive and a negative part. So one of them is here and the other one is there. And this should be equal to sigma of phi, where phi is just a section of W plus. Unfortunately, somehow the two form, the connection one form is a Lie algebra valued one form. It's not a real form. It's like I times a form. So there is a little I in here, but that's not so important. So this is the second equation. So that was pretty fast. I'm not sure how useful that was, but nevertheless, the upshot is that we start with a four manifold, we pick a metric on that, and we have to fix a spin C structure. And once we are done, once we done this, we have two equations. The first one is the Dirac equation, and then there is another one, which is for the curvature of the connection, not for the entire curvature, sort of half of the curvature. It splits into two pieces. This is where the 4D phenomenon happens. And for half of the curvature, we have a condition. So I will just copy this here.
Did you mean to say you turn a section into an element or a section into a section? By
Sorry.
section.
Yeah, section into a section. So these are the two equations. There is no reason to expect that the solutions will have any content of the differential topology of the manifold unless you are a physicist. And their explanation, I'm still puzzled by that. They said that you take the Johnson equations and you go to the ultraviolet or the infrared or whichever limit, and this is what you got. So do that. And consider the solution space of this equation. So now there is the principle as I was explaining or indicating, count solutions of these PDEs. Well, now we have to explain. So we explain, or I gave an outline of what the PDE is. What do you mean by count? That's the other thing. It turns out that if you have one solution, you have a whole bunch of solutions. That's a little problem. Here is the fact. Take the group G, which is just maps from X to S1. C infinity maps from the manifold to S1. And this has an action, G acts on the pairs A phi as follows. So A is a connection, so we can send it to A plus a one form, which is just G dG if G is an element here. So we can just take the one form associated to this function. This is a circle valued function, and we multiply with G, and phi should be sent to G times phi.
Sorry, we have to have inverse of G for one of them, yes.
Yes, sorry. We have this action on these pairs, and the fact is that if A phi solves this equation, Seibert-Whitner, then so does this G applied to the pair. And you can see that, I mean, there are a lot of such functions. This is like an uncountably many functions like this. So you would expect that if you have one solution, then you have too many. So this group is called the gauge group. And this is where the theory got its name. So we would like to count solutions up to this gauge equivalence. So instead of taking solutions, consider two spaces. B should be all pairs A phi divided by the reaction of this group. So these are all connections of that particular line bundle and all sections of W plus divided by this action. And M should be all solutions divided by this group. So clearly M sits in B. Okay, so this is how we will count. So far it was mostly topology with a little differential geometry. And this is where the complication starts. Because we would like to say that indeed, this guy represents a homology element in B. So the first observation is that this B is homotopy equivalent to CP infinity. I mean, this is not absolutely true, but I always assume that X is simply connected. Then it's true, and if X has some fundamental group, then you have to modify it a little bit, but yeah. So H star of B with Z coefficients is just Z generated by, I don't know, X, where X is in H2. Yes?
Is the first time you used that it's simply connected? Until now, that was not at all important.
No, until now, the construction worked perfectly for everything. I forgot to mention one thing. So we start with a Riemannian metric, and we know that every smooth manifold admits a Riemannian metric. And we also started with a spin C structure. Not every smooth manifold admits a spin C structure, but every four-dimensional manifold does. So that's an absolutely fair start. So this is in the second homology. So this shows that now I could write that. Let's do this. It just says that if this M happens to be a compact manifold of a smooth compact manifold of odd dimension, then we are in bad luck. And it will sit in a homology group, which is just zero, so we don't get any information. But if it happens to be an even dimensional space, then it sits in a even degree homology, which is isomorphic to Z, so we can turn it into a number. And this is exactly what we would like to do. So here's a fact. No, I say a dream. M is a compact manifold of dimension, D, which is just 1/4 C1 of this spin C structure. Remember that we had this W plus and W minus, the determinant line bundle was isomorphic, and this is just that determinant line bundle minus some topological terms, which happens to be congruent to B2 plus 1 mod 2 if pi 1 is trivial. We don't need pi 1 to be trivial here. B1 equals 0 would be enough.
Sorry, C1 is square.
C1 squared, sorry. So this is the first Chern class. If you take the square, you can integrate it against the fundamental class of the manifold, and then you get a number, and this is just the dimension. So you see that sort of half of the manifolds are sort of less interesting from this point of view. If B2 plus is even, then this is an odd number, so the dimension is odd, so M sits in the wrong homology group, and it just gives 0. But on the other hand, if this B2 plus is odd, as it happens for simply connected symplectic manifolds or symplectic manifolds, then we have an M sitting in an even dimensional homology, which is isomorphic to Z. Well, there are two isomorphisms, so you get a number up to sign. And that's your Seiberg-Witten invariant. Now, I said it's a dream because somehow we are taking the solution of a differential equation, or more generally an equation. And we know that in order to have some nice structure on a solution set of an equation, you need some kind of transversality. It already goes back to like high school or maybe before, like primary school mathematics. Like you take the parabola and how many solutions do we have? Well, if you take a generic parabola, we will have two. But if this is like the standard one, y equals x squared, then we have only one. But we usually say that you have to count it like with multiplicity 2 or something. So the problem is that the way this parabola intersects this line is not transverse, it's tangential. And very similar phenomena can happen here. Of course, you know, everything is much higher dimensional, so much more complicated problems can happen. And then this solution set will not be a manifold. In order to rectify that, what people usually do, so how do you prove that the solution set of an equation is a manifold? You use the implicit function theorem. The implicit function theorem demands that the derivative should be an onto function. And if it's not, you might sort of fix it up. So you just add some perturbation term here by adding a randomly chosen element or section of this bundle. And then you hope that although somehow the space changed a bit, but at the end of the day, the number you squeeze out will not. And this is exactly what happens. So this is only a dream that it will be a compact smooth manifold, but by modifying the equation a little bit, you can achieve that. Okay. So this is how we get, so the upshot is, so what was the input? The four manifold, the metric, the spin C structure, and then the output is this. Okay, I forgot to mention one thing. It's not only a compact manifold, but it's orientable. And in fact, you can pick an orientation by fixing some extra data, which I will not go into. You get a fundamental class in H, D of B, Z, which is isomorphic to Z if D is even. And then you just get a number. So Seiberg-Witten X of S is this number. Okay, so the real disturbing thing might be that we had to use this perturbation term. So we would like to say that the end result will be independent of that. And we also picked the metric. So I was campaigning against the Laplacian because it depends on the metric. Now I came up with something which also depends on the metric. So you might have your doubts, but it turns out, so this is the theorem, that if this B2 plus invariant, which already played some role in the parity of the moduli space, is bigger than 1, then this value will be independent of G of the choice of G and delta. So no matter which perturbation we take and no matter which metric which we started this procedure with, you will get always the same number. So, i.e., it is an invariant of X and of course, and of S. So at the end of the day, we get a function Seiberg-Witten from spin C of X, all the spin C structures on X to Z. Now this seems like a weird set. It is a weird set. But, and I promise you a function on age upper 2. And then I finish with this one last fact. So there are two functions two in quotation mark from spin C 4 to age upper 2 of x z. The first is what we already used. So you take a spin C structure, it comes as a pile of data, W plus, W minus, they have the isomorphic determinant bundles, and then there is this further isomorphism on bundles. But let's take just the determinant bundle and associate to it C1 of the determinant of W plus or W minus, doesn't matter. This is a map which is very natural, but unfortunately it's not an isomorphism. So the image consists of characteristic elements only. Indeed, every characteristic element gives rise to a spin C structure with that particular C1, and the non-characteristic elements just don't play. And also, there is this little problem that S is not uniquely determined by C1, provided the group has two torsion. So it's not a one-to-one correspondence. And there is another one saying that pick your favorite spin C structure and send it to 0. And then any other S differs from S0 by some element C in the second cohomology. So send. This is a very roundabout way to say something very simple, which I will say in a second. Then we send S to C. So what I want to say is that, sorry, it's X, right? That this set of spin C structures is kind of an affine space for that. So, you know, like in the plane, if you take a line not passing through the origin, it's still isomorphic to the line, but you have to tell me which element of this guy corresponds to the origin, and then everything is sort of, then there is a one-to-one correspondence. It's exactly the same. You have to pick your favorite spin C structure, you match it with the origin, and then everything is sort of one-to-one. So this is one-to-one, but depends on a choice. This doesn't depend on a choice, but not one-to-one. It's up to you to decide. If X happens to be symplectic, then it comes with a prescribed natural choice for S0. So then this identification is more natural. In general, it's not. So we are halfway through. And I will use the last minute to say that, so this is what I plan to cover. The theorem is that if we have a sigma in X, 4-dimensional manifold, 2-dimensional submanifold, everybody is oriented, and sigma self-intersection is non-negative, and the cyberwidth of X at the cohomology class K is not equal to 0, then K on sigma plus sigma squared is less than twice the genus minus 2. And I will just in one sentence, I will tell you how the proof would work. So first of all, we reduce to the case where the self-intersection is 0. So we have our manifold X, there is this sigma, and now I assume that the self-intersection is 0, and I will take a sequence of metrics. And since this number is independent of the metric, and it's never 0, we know that for every such metric, we will have a Cyber-Witten solution. And then some Chern-Weil theory will sort of lead us to this inequality in general. I'm sorry I took too much time on introducing, maybe it was a mission which I was not ready for, but what I really would like to convince you about is that, play around with these groups, play around with the bundles, make yourself familiar with these differential geometry notions like connections and sections of these bundles, and see how they match and how they are different. And at the end of the day, we get some equation, and it turns out that we can use those to actually understand topological properties of four manifolds. So this is where I will stop, and I will leave the rest for you guys. And also, the other reason I picked this topic is that in the TA session, you will meet a real expert, so you can torture him with those questions. And that's not my problem. Okay? Thank you.
Excuse me, what is the K inside study?
Say it again.
It is study of K.
So it's like K is just the first Chern class of some spin C structure for which the Cyber-Witten value is not equal to 0. So this is not 0. We don't really need that the value is not 0. What we really need is that for every such metric, we do have a Cyber-Witten solution. Okay. Yes.
Maybe I just got like lost somewhere along the way, but we were supposed to count solutions, but we took some element and then ascribed a number. Like, where's the count?
So we took this class. Okay,
Yeah.
so first of all, how do you count elements of a space, say, which looks like the torus? Like there are infinitely many of those. So we have to make a number out of that. And the idea is to look this guy inside the homology of a bigger space. Now, what happens if D is equal to 0? Which I have to add, it's always the case. So far, we only saw manifolds where this happens. Then it's really a count. Then you just have a 0-dimensional manifold with an orientation, and then you count them. What is an orientation, a 0-dimensional manifold? It's like a bunch of points, and there are signs assigned to them, and you just sum them up. So in this very special case, which is like 99% of for everyday practice, we just have really a count. But in general, it might not be the case, and then we do this homological thing. So this is why I said count. This is my way of counting. Yes, Dave.
So I mean, this was lightning introduction to basic Cyber-Witten. This hypothetical question, if you were going to tell us about Cyber-Witten with parameters, I guess family Cyber-Witten, how much more would you have to add to this introductory lecture? Or is it all the same?
I have no idea. I never lectured about this family Cyber-Witten. I don't know. But yeah.
I mean, it might just be the tiny bit more.
I don't think so.